Hey, how's everyone doing? This is Mr. Chavla or Mr. C, and in today's video, I'm going to be going over the part 2 key of the August 2016 Common Core Algebra 2 exam. So that's numbers 25 through 32. I'm going to try to fit it all into this video. If not, I might do maybe half of it in this video and then the other half in the other video. So this is the part 2 key, numbers 25 through 32 for the August 2016 Common Core Algebra 2 exam. And this is Mr. Chavla or Mr. C. Let's get started. Okay, number 25. Let me pull up my highlighter. So the volume of air, I'm going to just underline actually I got the highlighter. The volume of air in a person's lungs as the person breathes in and out can be modeled by a sine graph or a sine curve. A scientist is studying the differences in this volume for two groups, for people at rest compared to people taking a deep breath or told to take a deep breath. When examining the graph, should the scientist focus on the amplitude or should he focus on the period or the midline? And explain your choice. So what we need to know, guys, is first of all, you need to know your basic trig, like the properties of the trig graph, what the amplitude, period, and midline are. But assuming you know that, right? If I have a sine curve, just any old sine curve, right? It looks something like this. Not like that. And I'll use red. It looks something like this if I graph one cycle. Something like that, right? It's not exactly, I kind of messed it up. Right, something like that, where here I have what's known as the midline. It goes in cycles. That's why the volume of air can be modeled by sine graph, because you breathe in cycles. Breathe in, breathe out, and then repeat. So that's one cycle, and then we have another cycle, right? So let's talk about what each part of a graph represents and then what it represents in this context. So first thing, the midline is the average value of the sine curve. The average value, right? AVG for average. But on the y-axis, we're going to have volume with respect to time in seconds. So the midline then is the average height of the curve, right? That's the average volume of air in a person's lungs. Okay? Then the amplitude just tells me how much does the volume increase from the midline to the maximum. And that's going to be the same distance it decreases, right? So that's the amplitude. So I'll put that one in red. The amplitude in a sine curve, it's just in any sine curve, it tells how much the graph goes up and down from the midline. So if the amplitude was 3, it goes up 3 from the midline to get to the maximum, and then down 3 from the midline to get to the minimum. So this is the min, and this is the max, right? So in this context, it's volume, so it just tells basically the increase and decrease in volume, right? What's the distance or the amount the volume increases when you breathe in compared to the midline, and what's the volume it decreases, sorry, wrong way, when you breathe out, and that amount will be the same. So if it increases by 3 units or 3, I don't know what the volume is going to be measured in from the midline, it's also going to decrease by 3 as it goes to the minimum. So increase by 3 to go to the maximum, decrease by 3 to go to the minimum. In a sine curve, that doesn't change, right? Then the period is just the length of one's it's the time it takes the curve to complete one cycle, right? Because if I were to do this again, I would repeat another cycle. So the period is, in this case, is one breath cycle. The time it takes to complete one breath cycle. So this value right here, when we complete a cycle and return to the midline, is our period. So the period, I'll do in blue. The period is the time to complete one breath cycle. All right, let me minimize me for now. Okay, so let's go ahead and read the question again. So the volume of air can be modeled by sine graph, and now we understand why, because of the repetitive nature of breathing, right? The cyclical nature as volume goes up, then it comes down, then it comes down as you really exhale, and then it comes back up, right? So the volume of air in a person's lungs as they breathe in, and it increases out and it decreases, can be modeled by sine graph. And now we understand why. A scientist is studying the differences in this volume for people at rest compared to people told to take a deep breath. So the first thing, guys, before I even look at the next part, if I'm talking about the differences in volume, the period is talking about the time to complete a breath cycle. That has nothing to do with the difference in volume itself. So even if that's different, that's not going to help us with this one. So now let's see what it would look like. When a person takes a deep breath, do they inhale, if they're inhaling more deeply, so let's say this graph was at rest, right? The one we just drew was at rest. Then let's say what a person who's taking a deep breath would look like. For all I know, the average volume might be the same, but I know that the extent to which it increases as they inhale will be much more, and as they exhale will be much more as well, right? So that's the amplitude will rise more. The midline, I don't know if that'll be different. So if, let's say I'll just draw another one who's at rest. Let's say the midline might be the same. I don't know, and it could be different for different people. That's hard to compare. But if you're taking shallower breaths and you're at rest, just breathing normally, your amplitude's not going to be as much. So if you're talking about the difference in volume, it's definitely not the period and most likely not the midline because it doesn't give us as much information. The main difference you see is in the amplitude. How much air is being taken in when you inhale and how much air is leaving the lungs as you exhale. So you didn't have to do all this. This was for me to help explain. Pause the video if you need to. Make sure you understand this. I'm going to go ahead and answer the question now. Okay? Because I need space. I just used all this up. If you wanted to do this kind of work, I mean, nothing wrong with that. You would do it on scrap paper. Or you wouldn't write as big as I'm writing right now. But basically what you're gonna say is that the scientists should focus on the amplitude because the differences in the volume is talking about the increase and decrease, right? And that's the difference you see for people at rest versus when they're taking a deep breath. So when examining the graph, so you want to study the difference in volume for people at rest compared to taking a deep breath. When examining the graph, should the scientists focus on the amplitude? Then explain your choice. Okay, so do you focus on the amplitude, period, and midline? You should focus on the amplitude. Now we're going to explain our choice. Because it shows how much the volume increases. And we should say volume of air in the lungs. I'll minimize me again, I'm sorry. It shows how much the volume of air in the lungs. So it shows how much the volume of air in the lungs increases and decreases that's the difference we're talking about, right? For a person at rest compared to a person taking a deep breath. All right, this is for a person at rest. It doesn't increase and decrease as much, but when they're taking a deep breath, it increases and decreases a lot more. All right, so let's make sure we answer the question. So the volume of air in a person's lungs as they breathe in and out can be modeled by a sine curve. A scientist studying the differences in this volume for people at rest compared to people taking a deep breath. When examining the graphs, should the scientist focus on the amplitude, period, or midline? We said this scientist should focus on the amplitude, right? Not any of these two. So should the scientist focus on the amplitude and then explain your. So we answered this part of the question. Explain your choice because it shows how much the volume of air in the lungs increases and decreases. That's the difference for a person at rest compared to a person taking a deep breath. So we explained our choice as well. Okay. So I'm gonna see if I could fit everything in the whole screen without making it so small. And let's erase my markings. And the more you know about sine and cosine curves and what they represent, the more quickly and easily you could answer this question. I did not like the way it was worded too much though, but here we go, guys. And let me pull myself up for a while too. Here we go, I'm back. Does this make sense, guys? So make sure you understand what a sine and cosine curve looks like, what its properties are, amplitude, period, and midline. and what it represents in different contexts, okay? So that was number 25. We're going to move on to 26. So explain how the expression 3 to the 1/5 squared, so that's our original expression, can be rewritten as the equivalent radical expression 5th root of 9. So we need to have some middle steps. One of the things you could do, guys, is if you know the taking the fifth, raising a number to the 1 over any power is the same as taking the 5th root of that number. I'm sorry, raising a number to the 1 over any power is the same as taking that root of that number, right? So that means we're taking the 5th root of 3, but we're also squaring it as well. We could apply it in any order, so we could also square the 3 first. So it doesn't matter if you change it to the 5th root first or you square it first, but we could switch the exponents, because at the end of the day, if I have the 5th root of 3, that's what the 3 to the 1/5 power is. It doesn't matter if I do that first or if I square the 3 first, right? And so this becomes 9 to the 1/5. Let's make it clear. Let's follow one path, okay? So let's say I apply the exponents in reverse order. So the 2 and the 1/5 are reversed. 3 squared is 9, so it becomes 9 to the 1/5. Raising to the 1/5 power, anything to the 1/5 or 1 over anything power, this number goes in the root, is the 5th root. So that becomes 5th root of 9. So let's keep it simple. It's a 2-point question, and there were other ways to do it as well, but let's go ahead and answer this. So the exponents can be applied in either order. So I reversed the exponents to get 3 squared to the 1/5. Squaring 3 yields 9. So I rewrote 3 squared to the 1/5 as 9 to the 1/5. And then the last part is that raising to the 1/5 power is the same as taking the 1/5 root. Raising a quantity to the 1/5 power is the same or equivalent taking the 5th root of that quantity. So 9 to the 1/5 power can be written as the 5th root of 9. All right, there were other ways to do that as well. Let's make sure it checks out. So the exponents can be applied in either order, so I reversed the exponents, or the order of the exponents, to get 3 squared to the 1/5. So 3 to the 1/5 squared becomes 3 squared to the 1/5. Squaring 3 yields 9. So I rewrote 3 squared to the 1/5 as 9 to the 1/5. Raising the quantity to the 1/5 power is the same as taking the 5th root of that quantity. So 9 to the 1/5 power can be written as the 5th root of 9. Yes. So guys, there were multiple ways to do this, and explain. This was one way, one out of at least 3 or 4, if not more. Now I'm trying to get this all to fit in the screen, and I hope it's not getting too small. I'm gonna see if I can. Okay, so can I get this to fit, please? Okay, this is the best I could do, guys. You're gonna have to scroll back and forth, okay? I don't know if this is gonna come out too small. Maybe if I make this window smaller? No, that doesn't help at all. I'm gonna minimize me too, because I don't want to be in the way here. I guess I could have used more space horizontally. Alright, guys, make sure you got this. Alright, and there were other ways to do it. If you want to know, let me know or look it up yourself, and I could show you other ways this could have been done too. Okay, but that was 26. We're good to go. I just like to check it off to make sure that we completed everything. So explain how it could be rewritten, and we did, and we even justified our response by showing work here. Alright, and that was many ways to do it. I'm sure there were like quicker ways to do it as well. But I just don't I'm a little reluctant to take shortcuts sometimes, for fear of like losing points, and I wouldn't want that to happen to you, okay? All right, so let's move along. Number 27. Simplify x times I minus 7i squared, where I is the imaginary unit. So remember this, guys. I is equal to the square root of -1. It's an imaginary number because you can't take the square root of a negative number in the real number system because that would result in an imaginary number, right? And when you square both sides, you know that I squared is equal to the value -1. So instead of distributing, let's take this shortcut, guys, where we have xi. I'll put a 1 in front of this I for the coefficient. 1i minus 7i squared. I could have used parentheses instead of brackets, but 1 minus 7 is -6. So this becomes -6i squared. Now, and we bring down the xi. When I square -6i, guys, -6 times -6 is positive 36. And then I square I to get I squared. Let's just use the fact that I squared equals -1 and rewrite this as xi times 36 times -1. Now I know I was putting the brackets earlier. Okay, so this becomes xi, if we're showing all steps, I don't know how much we have to show exactly, times -36, which if we rewrite it in standard form, it's -36 xi, where the I comes last. And that's the simplified form, okay? So simplify this where I is the imaginary unit, done. Okay, that was one way to do it. I would not want to distribute the I minus 7i, not just because that could lead to errors, but it's a lot of extra work that's not necessary, all right? If you got the same answer, make sure that you still use the correct procedure because there were other ways to do it, whether you distributed I minus 7i without simplifying first, or you might have simplified and got, you distribute xi and get 36i cubed, that's fine too, as long as you understand that it at the end and how it gets to -36xi, okay? So we're going to go on to number 28. And I'm still going to keep myself minimized because I don't want to block anything. Okay, so using the identity sine square of theta, that's the same as saying the sine of theta being squared plus cosine squared theta equals 1. Find the value of tangent theta to the nearest hundredth. That's to 2 decimal places. If cosine theta is -0.7 and theta is in quadrant 2. So first thing we want to do, guys, is let's make sure we have our quadrants clear, that we know what that is. So here's quadrant 1, here's quadrant 2, 3, and 4. There's an acronym. It goes add sugar to coffee. This means A means all positive, sine, cosine, and tangent in the first quadrant. This means that only sine is positive, the others are negative. That's why cosine theta is negative in quadrant 2. All right? But sine will be positive. So we have to find the value of sine theta first, making sure it'll be positive, and then we'll find tan theta. So let's find sine theta first. And then the fact that tangent, we'll use this rule, and then we'll use the fact that tangent theta is equal to sine theta over cosine theta. That's the way that I thought about doing it, all right? There might have been other ways, but let's do this first. So sine square of theta plus cosine square of theta is equal to 1. So I'm going to replace cosine squared theta with -0.7. All right. Now, what I want to do next is square negative 0.7, which if you were to put in the calculator, or if you know how to do it by hand, becomes 0.49 or 0.49. Okay? Then I subtract 0.49 on both sides of the equation. So I subtract it, and then 1 minus 0.49 is 0.51. Now, how do I get rid of square? I have to take the square root. Usually we take positive and negative, but sine has to be positive in quadrant 2, so sine theta is going to equal positive square root of 0.51 in quadrant 2. And then we're going to use, I'm not going to simplify this because they want to the nearest hundredth and they want tangent theta, right? So now I'm going to use this rule. So remember, tan will have to be negative because anything that's not sine theta out of sine, cosine, tan will be negative in the second quadrant. So that'll check out. If I substitute square root of 0.51, that's positive for sine theta, making sure only this is in the square root sign. And they told us that cosine theta is negative 0.7 or negative 0.7. And I'm going to put it like that in the calculator, and then they want the value to the nearest hundredth. Right, that's to 2 decimal places. So let's go ahead and put this in our calculator. Sorry, guys. The fraction, square root of 0.51 on top. All over negative 0.7. And to the nearest hundredth, that's 2 decimal places, we get negative 1.02. So I'll write my final answer here that tan of theta, or tangent theta, is equal to approximately negative 1.02. Yeah, I was looking at the answer keys on JMap because I have a bad habit sometimes of over-explaining things because I don't like when people lose points for under-explaining. So I was trying to see if one of the sample responses by a student in the sample response set, not on JMap, on the Regents New York State website, I wanted to see if anybody had a brief way, because sometimes students come up with very nice, like quick, brief ways of explaining things, so that I could condense my explanation. So I was looking at those two and then added my perspective to it, because my explanation originally was too long when I was looking through the test. All right. So guys, here's number 28. Let's make sure we answered everything. Using the identity sine square plus cosine square is 1, we did. Find the value of tangent theta to the nearest hundredth. We got it right here. If cosine theta is negative 0.7 and theta is in quadrant 2, meaning tan should be negative. Got it. All right. Pause the video if you need to. I'm going to pull myself back up too. Hey. I try to keep myself in the video as well, but I don't like blocking the way. Okay, let's move on to number 29. I think we're making good pace. Okay, Elizabeth waited for 6 minutes. So she waited for 6 minutes at the drive-thru of her favorite fast food restaurant the last time she visited. She was upset about having to wait that long, so she felt like it was too long, and notified the manager. The manager assured her that the experience was very unusual and that it would not happen again. There are 2 parts. Okay, so let's look at the next part. A study of customers commissioned by this restaurant found an approximately normal distribution of results. The mean wait time was 226 seconds, and the standard deviation was 38 seconds. Given these data and using a 95% level of confidence, was her wait time unusual? Justify your answer. So the part which we're trying to answer, I'll just put it in blue. So was her wait time unusual? And then justify your answer. So guys, in a normal distribution, 95% of the data lie within approximately 2 standard deviations of the mean. So we know it's a normal distribution, and it's going to be 2 standard deviations of the mean. So the mean, which I'll use this symbol, the mean wait time was 226, and very important to look at the units, seconds. And the standard deviation, when they did a study of all the customers, was, so the mean 226 and the standard deviation was 38 seconds. The 95% confidence interval is the range of results that we would expect people to wait. Like, what's the normal wait time? 95% of the time you could expect to wait between such and such amount of time, right? So it's going to be the mean, 226, plus and minus 2 standard deviations, which is 38. All right? So I'm going to just put it directly in the calculator. So it'll be minimize me, 226 minus 2 times 38 is 150. 226 plus 2 times 38 is 302. So it's 150 to 302 seconds. So that's going to be 150 seconds to 302 seconds. And that's our 95% confidence interval, right? So her wait time was 6 minutes. 6 minutes is equal to 360 seconds. So Elizabeth waited for 6 minutes, right? Times 60 seconds per minute, that's 360 seconds. So anything that's inside the 95% confidence interval is something that we would normally expect. All right? If it's below, it's unusually low, like maybe you got really lucky. If it's above, that means it was unusually long. That's not to be expected most of the time, right? If it's more than 2 standard deviations above the mean, which is 202 seconds. So we're just going to say the question was, remember I said I highlighted in blue or green? It turned green because I mixed blue and yellow. Was her wait time unusual? Absolutely. Her wait time was very unusual. As or because it was above, see, it was longer than 302 seconds, the 95% confidence interval. Wow, I ran out of space. Okay, then what I'm going to do is I'm going to just rewrite this, guys. I'm going to rewrite it so that I can fit it to the screen. So the mean plus minus 2 standard deviations is 226 plus minus 2 times 38, which gives us 150 to 302 seconds, right? This is the 95% confidence, minimize me again, interval or level. All right, and then, sorry guys, I didn't mean to do this. I didn't realize I was running out of space. Because in like some previous videos, I was kind of smushing up too much space. So 95% confidence interval. So Elizabeth waited for 360 seconds, right? So was her wait time unusual? Yeah, her wait time was unusual as it was above the 95% confidence interval. And let's just make this a complete sentence, so as part of our justification. Elizabeth waited for 360 seconds. Okay, So we gave a complete incorrect response, all right? So was her wait time unusual? Her wait time was unusual. So we said yes, her wait time was unusual as it was above the 95% confidence interval. All right, so we said yes and why. Okay, and we showed our work. So we did a complete justification. That was one way to do it. There were a few other ways as well, but we don't need to know all of them, right? This was the most like basic fundamental way that I could think of is calculate the 95% confidence interval. If it's within that range, it's not unusual. If it's above, it was unusually high or unusually long in this case because it was above the 95%. If it was below, it was unusually low, right? So, but 95% of the time, we expect the wait time to be somewhere between 150 to 302 seconds. That's the typical wait time in this fast food restaurant for um, people going through the drive-through. That you would normally expect, it's a normal, on a normal day, you expect people to wait somewhere from 150 to 302 seconds with an average of 226 seconds, right? 95% of the time. All right, next question. This is all knowing about like 95% confidence intervals and normal distribution. Well, I like this question. The x value of which functions x-intercept is larger, f or h, and justify your answer. So guys, x-intercept is the value where y equals 0. So if I have a graph, the y-intercept is where x is 0, right? It'll be like, let's say it's a linear graph. Remember y equals mx plus b. The y-intercept is 0, comma b. The x-intercept is where y equals 0. So let's find the so or where f of x is 0, right? So h of x, see, this is your y-intercept. 0, 4, when x is 0, y is 4, is the y-intercept. That's not what we want. So we don't want this, we want the x-intercept. And the x value of the x-intercept is 2. So the x-intercept is 2, 0, and the x value equals 2. So let's see if which one has a larger, the x value of which function's x-intercept is larger, f or h. So this is for h of x. Now let's find out for f of x. So we could do this algebraically. We could have made a table of values, a graph, basically just want to find the roots. So what do we want to replace f of x with? We want to see where f of x equals 0, because the y value has to be 0. Like this one, h of 2 equals 0, right? So 0 equals log. When I don't have a number here, guys, when I'm taking logs, common log, the base is just 10. And we have x minus 4 in parentheses. What we want is, this is the base, right? The 10. This x minus 4 is what we actually wanted to end up equaling. And then we have the exponent here. So it's saying 10 to the 0 power is equal to x minus 4, right? So anything to the 0 power is 1. So 10 to the 0 is 1. If x minus 4 equals 1, x equals 5. So the x-intercept for this one is 5, comma 0, and the x value is 5. All right, so for this one, it's 2. So I'll just write x equals 2. Right? You could have also sketched a graph of this, but it's hard to do without a grid. But even then, you didn't have to do a perfect graph, just a small like little sketch where you show the x-intercept is 5. Wow, that's a mess. So the x-intercept is 2, comma 0, and x equals 2. And for this one, it's 5, comma 0, and x equals 5. So the x value of which function's x-intercept is larger, f or h? Well, for f it's 5, and for h it's 2. So the x value of f of x is x-intercept is larger. So f, since 5 is greater than 2. Right? So the x value of which function's x-intercept is larger? F of x. Because 5 is greater than 2. Right? Justify your answer, and we did. That's all there was to it, guys. All right, I think I'll be able to finish this video, part 2 in this video alone. So let's move on to 31. And again, you could have used a table of values for f of x or graph, sketched a graph, but I thought algebraic was kind of quick for this one if you know how to use your logarithms. All right, moving along to number 31. The distance needed to stop a car after applying the brakes varies directly with the square of the car's speed. That's the other thing we're looking at. Basically we're looking at the car's speed over here, and the distance needed to stop the car is over here. Okay, so basically, let's see, the table below shows stopping distance. That's right here in feet for various speeds in mile per hour. So as we see, the speeds are just going up by 10 miles per hour each time, 10, 20, 30, 40, 50, 60, 70. And then the distance is also increasing. We don't really need to look for a pattern right now. So 6.25, 25, 56.25, 100, and so on. And it's increasing, right? Determine that, and that makes sense. As you drive faster, if you're driving faster, the distance you need to stop the car, the car will travel a larger distance as you're applying the brakes before coming to a full stop, assuming you don't slam the brakes, right? So let's see what it says. So basically the speed is like your x value, right? And as your speed increases, the distance that you need to stop the car also increases. That's called the braking distance. So find the average rate of change in braking distance. So that's like your y value in feet per, and the unit is feet per mile per hour, between a car traveling at 50 miles per hour, so those are the speeds, right? And one traveling at 70 miles per hour. So the change in speed is plus 20 miles per hour, right? So it's going to be the change, remember that they want the change in braking distance, right? So it'll be the change in distance, I'll call that d, over change in speed, which I'll call s. The distance meaning the braking distance. So the speed increased by 20 miles per hour, right? Or I'll even show the, no, we don't need to do that. 70 minus 50 is 20, right? If you wanted to show it that way, we could do it that way as well. The 70 minus 50, because that's what I'm going to do on the top. On the top, I want to take the braking distance at 50 miles per hour and 70 miles per hour and see how much that went up by, which you'll see is 150. If I do 306.25 minus 156.25, you could just put that in the calculator, right? Or not, if you, I would suggest put in the calculator, just make it quick and avoid errors, right? So 306.25 minus 156.25 is 150. So it becomes 150 is the feet, right? So this went up by 120, by 150 feet, the distance needed to stop the car. So 150 feet over 20 miles per hour. So if we divide 150 by 20 now, you get 7.5. So it's 7.5 feet per mile per hour. All right, I won't put the units here. I'll write the answer here. So 7.5 feet per mile per hour. So that's as the car's speed increases by 20 miles per hour from 50 to 70 miles per hour, the distance needed to stop the car increased by 150 additional feet, right? A car traveling at 70 miles per hour needed 150 more feet to stop than one traveling at 50. But on average, it increases as you increase from 50 to 70 miles per hour. The distance needed to stop the car increases on average by 7.5 feet for each 1 mile per hour increase in speed, which brings us to the next part. So determine the average rate of change in braking distance in feet per mile per hour between a car traveling at 50 and 70 miles per hour. We just did that part, right? Now explain what this rate of change means as it relates to braking distance. This is what I was just talking about. Explain what this rate of change means as it relates to the braking distance. So as the speed of a car increases from 50 miles per hour to 70 miles per hour, the distance needed to stop the car. That's what the braking distance is. After applying the brakes, since it's a positive, right, and that makes sense, it increases. Now here's what we need to watch out for. We need to include the word average, all right? That's very important. By an average of 7.5 feet per mile per hour. That means on average, each 1 mile per hour increase in speed requires 7.5 additional feet to stop. It doesn't work exactly that way because it's not a linear function, but on average, the increase in braking distance is 7.5 feet per 1 mile per hour increase in speed. So let's make sure we answer this properly. So explain what this rate of change means as it relates to braking distance. As the speed of a car increased from 50 to 70 miles per hour, the distance needed to stop the car after applying the brakes, that's the braking distance, increases by an average of 7.5 feet per mile per hour. All right, that was it. I thought this would have been better for a 4-point question because it has multiple parts, but hey, let's make sure this all fits. Okay, so make sure you got this, guys, okay? I hope this makes sense to you. It's all about knowing rate of change and how to interpret it in different contexts, okay? So let's move along. And let's make sure we got everything. So since I'm in the habit now of checking things off as I complete it, let's check it off here too. We explained what it meant, the rate of change as it related to braking distance. And we're done with 31. Let's go on to the last one in this set, 32. Given events A and B such that probability of A is equal to 0.6, I'm going to minimize me again, and probability of B is 0.5, and probability of A, this means or, guys, okay? I'm going to write it as a side note. This means probability of A or B. That's what this symbol right here means, all right? That stands for union. We need to also know, so let's go ahead and write this down. So given events A and B such that probability of A is 0.6, probability of B is 0.5, and the probability of A or B or union B is 0.8, determine whether A and B are independent or dependent. We got to find out which one. So what we got to watch out for, guys, carefully, is we also need to know this symbol. Upside down U, like this means and. All right, so this is the probability of both A and B occurring. That's known as the intersection. Make sure you know what that means, right? So union, this is the union, this is intersection. So make sure you know what that means. And we had to be careful about this, okay? So look that up, and I'm gonna write the rule, okay? Because we need to find out what A or B is first. A and B is first, because A and B are independent if the probability of A and B intersection, right, is equal to the probability of A times the probability of B. So we need to find out if this is true, right? But before we do that, we need to find out what the probability of A and B is. So I'm gonna save this for later. We're gonna use a different rule that looks like this. The probability of A or B, right, is equal to the probability of A plus the probability of B minus the probability of A and B. Because both the probability of A and B include the things they have in common, so since we don't want to include it twice, which is included, we only want to include it once, we subtract it, okay? So we know the probability of A or B is 0.8, or I could just write 0.8, equals probability of A, which is 0.6, plus probability of B, which is 0.5, minus the probability of A and B. Now, if I add 0.6 and 0.5, I get 1.1 is equal to 1 minus probability of A and B is equal to 0.8. Now, if you think of it this way, guys, I'm going to add this value, probability of A and B, to both sides, and so that it just becomes positive probability of A and B on this side, right? if I add this on both sides. And I'm also going to subtract 0.8 on both sides, so that 1.1 minus 0.8 is 0.3. That saves me time, so I don't have to do as much work. So I got my answer just like that. But remember, I'm not done. So here's what I'm going to do. Remember that probability of A I want to now find out what's the probability of A times the probability of B. The probability of A is 0.6, right, or 0.6 times probability of B, which is 0.5 or a half. That becomes 0.3 or 0.3, right? They're equal. If probability of A and B is equal to the product of the probability of A and if the probability of A and or intersect B is equal to the probability of A times the probability of B, they're independent. If the product of probability of A times probability of B is not equal to the probability of A and B, then they're dependent. So we're going to say that A and B are independent as the probability of A and B is equal to the probability of A times the probability of B. There were other ways you could have done this by finding the conditional probabilities, but that would have been more work. So I said, let's not go that route, okay? This is called the product test for independence, okay? So given the events A and B such that probability of A is 0.6, the probability of B is 0.5 or a half, and the probability of A or B or intersect B, right, is equal to 0.8, determine whether A and B are independent or dependent. And we found that they are in fact independent, and we justified our answer, which they should have written here, justify your answer, because if they didn't, technically you should be able to say independent and get full credit, but that was not the case. So they should have said justify your answer, which we did. Okay? So this is about just knowing about the union and intersection of sets and probability rules, and then independence and dependent events. Okay? So guys, that was it for numbers 25 through 32. We were able to finish the part 2 part, which I'm thrilled. I hope you are too. Today is Sunday, July 28, 2019. For those of you who are taking the August exam, please study, do the best you can, right? I have a lot of faith in you. I have a lot of belief in you. If you're one of my students watching the video, or from Health Opportunities High School, or even if not, right? All of you guys, I wish you the best of luck, all right? From the bottom of my heart. Anything I could do to help you, let me know. Send me type a comment if you have a question on in the comment section below on YouTube, and I would appreciate if you would hit like, subscribe. That'll help me out. I'd really appreciate that. If not, of course, that's your choice, and I respect that. But I would really, really appreciate that. Okay, but that's all. That's all I have for today, guys. I mean, for now, I'm gonna go in the next video to continue part 3. All right. Thank you so much for stopping by. Best of luck.